In this video, we're going to be reviewing kinematics for AP Physics 1. We're going to start with scalars and vectors. Scalars are quantities that have magnitude only. Examples of these are distance and speed. Vectors are quantities that have magnitude and directions. Examples of these are displacement and velocity. Distance is the total ground covered. So this would be your odometer reading in your car. Displacement is the change in position. We can calculate this using the equation delta x is equal to the final position minus the initial position. Speed is how fast an object is moving, and the equation for average speed is distance over time. You'll notice there's a bar above the s that just means average. Velocity includes both speed and direction, and the equation for average velocity is displacement over time. Now we're going to take a look at an example. Here we have a numbered line. Imagine that we start from 1 and we go to 3. Each of these numbers represents a position measured in meters. So our initial position is 1 meter and we go to 3 meters. And then from 3 meters, we go in the negative direction to negative 1 meter. So the distance is the total ground covered. We went to the right 2 meters and we went to the left 4 meters. So 2 plus 4 is 6 meters. The displacement only cares about your initial and final position. It doesn't matter how you got there. So our final position is negative 1. Our initial position is 1. So negative 1 minus 1 equals negative 2 meters. To find the average speed, we're going to take the distance divided by the time. Let's say that this travel took us 6 seconds. So the distance is 6, the time is 6. So 6 divided by 6 is 1 meter per second. To calculate the average velocity, we take the displacement divided by the time. The displacement is negative 2 meters, the time is 6 seconds, and we get negative 0.33 meters per second. Now we'll take a look at an example that's two-dimensional. Let's say we go 3 meters east and 4 meters north. What is the distance? What is the displacement? So the distance would be 3 plus 4, which is 7 meters. That's the total ground covered. But the displacement only cares about your initial and final position. So notice that this is a right triangle, so we can use Pythagorean theorem. A squared plus b squared equals c squared. So if we take 3 squared plus 4 squared is equal to 5 squared. So that displacement is going to be 5 meters. Let's say you were to go in a circle. What would your displacement be? Since displacement is final position minus initial position, you're back to where you started. The displacement would be 0. Now we'll take a look at acceleration. Acceleration is the rate at which velocity changes over time. And you know something is accelerating if the object is speeding up, slowing down, or changing direction. If the acceleration and the velocity are in the same direction, then the object is speeding up. If the acceleration and velocity are in opposite direction, then you know that the object is slowing down. The equation for average acceleration is the change in velocity, delta v, divided by t. You can also write this as vf minus vi over t. The unit for acceleration is meters per second squared, or sometimes can be written as meters per second per second. If your acceleration was 3 meters per second squared, what that is saying is that every second the speed is changing by 3 meters per second. And now we're going to take a look at an acceleration problem. So here we have a car that starts off with an initial velocity of 5 meters per second and increases at a uniform rate to a velocity of 25 meters per second over a time period of 4 seconds. And we're going to calculate the acceleration using our equation, final velocity minus initial velocity divided by the time. We're going to substitute 25 for the final velocity, 5 for the initial, and 4 for the time. And we get 20 divided by 4, which is 5 meters per second squared. So if you take a look at this chart, it gives you an idea what 5 meters per second squared means. It means that every second the velocity is increasing by 5 meters per second. Now we're going to talk about motion graphs. On a position versus time graph, the steepness of the graph tells us the speed of the object. The slope of the graph tells us the velocity, and the velocity tells us not only how fast the object is moving, but also the direction. So it could be a positive slope, which means a positive velocity, or a negative slope, which means a negative velocity. On a velocity versus time graph, the slope represents the acceleration, and the area between the graph and the x-axis tells you the change in position or the displacement. Now, this area could be positive or the area could be negative, because you can have either a positive or negative displacement. On an acceleration versus time graph, the area between the graph and the x-axis represents the change in velocity. And once again, this could be a positive or a negative change in velocity. Now we'll take a look at some motion graphs. So on the first position versus time graph, you'll notice that we have this curved graph. To translate this to a velocity graph, we're going to look at the slope of the position graph. So you notice that at the beginning, there is a positive slope. So we know we're going to have a positive velocity. At the highest point of this position graph, you notice that it's flat. The slope of the tangent line is flat, and so the velocity is going to be 0. And at the end, the slope is negative, so we know we're going to have a negative velocity. Since we're dealing with constant acceleration, we know that the velocity graph is going to be a straight line, and in this case, it's slanted downward. Now, to translate this to an acceleration graph, we look at the slope on the velocity graph. Since it's slanted downward, this is a negative slope, so that means that the acceleration is going to be negative. Another way to represent motion is through motion maps, also known as dot diagrams. So we're using dots to represent the position of the object, and the distance between the dots tells us how fast the object is moving. And if the dots are getting closer, that means the object is slowing down. If the dots are getting further apart, that means the object is speeding up. And if you take a look at the position graph, you'll notice at the beginning the slope is getting less and less steep, and so we know it's slowing down and it's moving in the positive direction. So the dots are getting closer and closer in the positive direction. And then once it comes to a stop at an instant, it's going to turn around and it's going faster and faster, and so the dots are getting further and further apart. Here is another motion graph, and this one looks like a U. At the beginning part of this graph, you'll notice that it has a negative slope, so the velocity is going to be negative. At the midpoint of this graph, it's a flat line. The slope of the tangent is a flat line, so the velocity is 0. And then at the end of the graph, it has a positive velocity, or positive slope, and so it has a positive velocity. So to find the acceleration, we're going to look at the velocity graph, and the velocity graph is slanted upward. It's a positive slope, so the acceleration is also going to be positive. Now, the area under the velocity graph tells us the displacement, and what you notice is that in this case, the displacement at the first half of the trip is equal to the displacement the second half of the trip, except the displacement the first half is negative, displacement in the second half is positive. And so if you wanted to find the total displacement of this object's motion, it would be 0, because the first half cancels out the second half. Now, for the acceleration, the area under the curve is the change in velocity, and we have a positive change in velocity. So what's going on in this graph? So this object is going in the negative direction and slowing down to a stop, as you can see in the motion map, and then it turns around and it speeds up in the positive direction. So it's going the negative direction, slowing down to a stop, and then turns around and speeds up in the positive direction. Now we'll take a look at the kinematic equations. On the equation sheet, you'll see the first 3, but the fourth one can be helpful, but it's not on the equation sheet. So let's go through the variables, make sure that you know what each of the variables are. So delta x is displacement, vi is the initial velocity, vf is the final velocity, a is the acceleration, and t is time. You'll notice that for each equation, it has 4 variables. There are 5 possible variables, but each equation has 4 variables. And this equation chart is helpful to help us to figure out which equation to use. So when you're solving a problem, you want to write down all the variables that you're given and look at the variable that you're not using. And we're going to use that variable that you're not using as a clue to figure out which equation to use. So for example, if you're solving a problem and displacement, delta x, is not involved in the problem, then you would use VF equals VI plus AT. So now let's work out a kinematics equation problem. We have a car that's initially moving at 30 meters per second and slows down to a stop. And we're going to make right positive. The acceleration is negative 4 meters per second squared. We want to know the horizontal displacement. How far does it travel? So we're going to start with our variables chart, delta x, vi, vf, at. And we know that vi is 30 meters per second. Vf, our final velocity, is 0, and the acceleration is negative 4 meters per second. And we're looking for the displacement, so we're going to put a question mark there. And notice that t is not involved in this problem solving, so that's our clue to figure out which equation to use. So I'm going to go back to my chart and look at t, and then go down from where t is. We'll see that shaded in section and go to the left. We see our equation, vf squared equals vi squared plus 2a delta x. And so we're going to use that equation. So we're going to substitute our known variables and solve for the unknown for delta x, and we get 112.5 meters. Next, we're going to take a look at free fall. So when an object is in free fall, it means that it's falling only under the influence of gravity. And the acceleration due to gravity is approximately 10 meters per second squared. It's going to be downward. The more precise number is 9.81, but on the AP Physics 1 exam, 10 meters per second squared is accepted. So let's start with a ball that's dropping from rest. So we're going to use a motion map to represent this motion. As it's falling, it's going faster and faster. So you notice that the dots are getting farther and farther apart. At 1 second, the velocity is 10 meters per second. At 2 seconds, the velocity is 20 meters per second. At 3 seconds, the velocity is 30 meters per second. So when we say that the acceleration is 10 meters per second squared, what we're saying is that every second, the speed here is increasing by 10 meters per second. Now, what if we threw a ball up? Straight up. Okay, so a ball straight up and then coming back down. We're going to make up positive, and so as the ball is going up, it's going to have a positive velocity. So we're going to start off with 30 meters per second. 1 second later, it'll be 20 meters per second. 2 seconds later, it'll be 10 meters per second. 3 seconds later, it'll be at its peak height with 0 velocity, and then it's going to come back down. 1 second later, it'll be negative 10 meters per second. Another second later, it'll be negative 20 meters per second. And then another second later, it'll be negative 30 meters per second. Now we're going to solve a free fall problem where we throw a ball straight up into the air with the initial velocity of 20 meters per second. We're going to make up positive, and we want to find out what is the final velocity once the ball is 10 meters above the thrower's hand before it reaches the peak. So we're going to start with our variables chart, delta x, vi, vf, a, and t. The delta x displacement is 10 meters, vi is 20 meters per second. The final velocity is what we're looking for, so I'm going to put a question mark. The acceleration is negative 10 meters per second squared because I made up positive, and so the acceleration is downward, so it's going to be a negative number. We're going to find an equation that does not have t, and once again, that's going to be vf squared equals vi squared plus 2a delta y. We're going to substitute the known variables and solve for the unknown vf. Don't forget to square root because vf is squared, and we get that vf is equal to 14.1 meters per second. Next, we're going to take a look at projectile motion. So while free fall motion is dealing with one-dimensional motion up and down, projectile motion is dealing with 2 dimensions. It's not only moving up and down, but also left and right. For the horizontal motion, the acceleration is equal to 0. There's no acceleration, and so it has constant velocity. So for horizontal motion, we'll be using the equation delta x equals vt. And for the vertical motion, the acceleration is 10 meters per second squared down, and this is because gravity force is pulling it down. We'll talk about that later in dynamics. And so for vertical motion, you'll be using one of the kinematic equations to solve for the vertical motion. Now, before we actually look at a sample problem, I just want to quickly review SOHCAHTOA. You'll need to know these trig ratios to solve projectile motion problems where we have an object launched at an angle. So SOHCAHTOA is a mnemonic to help us remember these trig ratios. Sine theta is equal to opposite over hypotenuse. Cosine theta is equal to adjacent over hypotenuse. Tan theta is equal to opposite over adjacent. Also, the Pythagorean theorem will be useful to solve these projectile motion problems. And so just a quick review that a squared plus b squared is equal to c squared for right triangles. And now let's take a look at motion maps for projectile motion problems. So we have a cliff here, and we're launching a ball off the cliff horizontally. So this is a horizontally launched projectile motion. And so what you'll notice is that horizontally, the arrows have the same length, which tells you that the magnitude of the velocity horizontally is constant. So it has a constant horizontal velocity, but vertically, it's accelerating. So you can see that the green arrows are getting longer and longer. If the object is launched at an angle, the horizontal motion is also going to be constant velocity, while the vertical motion, vertical velocity, is going to be accelerating. On its way up, the vertical velocity decreases all the way up to the peak where it has 0 vertical velocity. And then as it's coming down, the vertical velocity increases downward. Notice at the peak, although there's no vertical velocity, there is still a horizontal velocity. So it is still moving the rightwards at the highest point. To find the speed at any point, you can combine the horizontal velocity and the vertical velocity using vector addition, as you see in the white arrow at the beginning of this projectile motion and at the end of the projectile motion. Now we're going to solve a projectile launched at an angle problem. Here we have a ball that we're kicking at an angle, and the ball is getting kicked at a speed of 15 meters per second at an angle of 30 degrees above the horizontal. We want to first calculate the initial velocity, the initial horizontal velocity, and the initial vertical velocity. So we need to do a little bit of trig. To find the vertical initial velocity, we're going to use sine, because sine is opposite over hypotenuse, and the opposite is Vy, and the hypotenuse is 15. Multiplying 15 on both sides gives us 15 sine 30, and we get 7.5 meters per second. To find the horizontal initial velocity, we're going to use cosine, which is adjacent over hypotenuse. The adjacent is Vx, the hypotenuse is 15, so Vx is equal to 15 cosine 30, which we get 13 meters per second. For part B, we're going to calculate the time that the ball is in the air, the flight time. And so we're going to create this chart here that has both a horizontal column and a vertical column. And we know that the initial velocity horizontally is 13 meters per second. We just calculated that. The final velocity will also be 13 meters per second because horizontally it's moving at constant velocity. The vertical initial velocity is 7.5 meters per second, which we just calculated. The acceleration is 0 because horizontally the object is not accelerating. For the acceleration vertically, we're going to set right positive in the x direction, and the y is going to be positive going up. And so with those positive directions, the acceleration will be negative 10 meters per second squared vertically because we made a positive, and we know that the acceleration due to gravity is down. Now our strategy for finding the flight time is to find the time to get to the peak height and then times 2, and then that will give you also the time to go all the way to the top and then all the way back down. So to find the time to get to the peak height, we know that the peak height, the velocity, the final velocity will be 0. So now we need to find an equation that has initial velocity, final velocity, and acceleration, but it does not have, and we're looking for time, but it doesn't have delta x. So that equation would be Vf equals Vi plus At. And substituting what we know, we get that t is equal to 0.75 seconds. Remember, this is half of the trip. It's from the ground to the highest point, but then it also needs to come back down to get the flight time. And so we take 0.75 times 2, and we get 1.5 seconds. For part C, we're looking for the maximum height. What is the peak height? What is that distance? So we're going to use Vf squared equals Vi squared plus 2a delta y. We're going to substitute our known variables and solve for delta y, which we get 2.81 meters. Lastly, we're looking for delta x, the horizontal displacement, also known as the range. Because horizontally the object is moving at constant velocity, we can use delta x equals Vt. Horizontally, we know that the velocity is 13 meters per second, and the time is 1.5. Notice that the vertical time and the horizontal time is equal to each other as long as you're looking at the same part of the motion. And so delta x equals Vt, we get 13 times 1.5, which gives us 19.5 meters. Next, we're going to take a look at relative motion. So motion is relative depending on your frame of reference, and sometimes frame of references are also moving, so we need a way to be able to solve these problems. The equation we're going to use is VAC is equal to VAB plus VBC. Let's take a look at the subscripts. Notice that it says AC and then it's AB, BC. Notice that the B's are next to each other and that the A is at the beginning, C is at the end. Keep this pattern in mind. We'll be using that to solve these problems. VAC stands for velocity of object A relative to object C. VAB is the velocity of object A relative to object B, and VBC is the velocity of object B relative to object C. In our problem, we have car A, which is traveling at 20 meters per second with respect to the ground, and car B, which is traveling at 25 meters per second with respect to the ground. And we want to know what is the velocity of car B with respect to A. So our subscript here is BA. So on the right-hand side, B is going to be in the beginning, A is going to be at the end, and the G is going to be in the middle. So we're going to write VBG plus VGA. VBG we know is 25 meters per second. But we don't have VGA. We have VAG. To switch those subscripts to VGA, we're going to flip the direction of the velocity. So instead of positive 20 meters per second, we're going to use a minus 20 meters per second. So we get 25 minus 20, we get 5 meters per second. So the velocity of car B with respect to A is going to be a positive 5 meters per second. Now we have a person in a train. The person in the train is moving to the right at 5 meters per second, but the train is also moving to the right at 20 meters per second. So the velocity of the person with respect to the train is 5 meters per second. The velocity of the train with respect to the ground is 20 meters per second. And we want to know what is the velocity of the person with respect to the ground. So the subscript on the right-hand side should start with the P, should end with a G. The train will be in the middle. So we have VPT plus VTG. VPT is the velocity of person with respect to the train, that's 5 meters per second. VTG is the velocity of the train with respect to the ground, and that's 20 meters per second. So 5 plus 20, and we get 25 meters per second. In this video, we're going to cover AP Physics 1 Unit 2. We're going to cover the first half, which is going to be on forces and Newton's laws. A force is a push or a pull, and the unit for force is newtons. We're going to take a look at some common types of forces. The first one is gravitational force. Another name for gravitational force is weight, and this is defined as the force of gravity. If you know the mass of an object, you can calculate the gravitational force by taking mass times g. Mass is the amount of matter in an object. If you take an object to the moon, the mass of the object will stay the same, but the gravitational force, the weight of the object, will be different because g, the gravitational field strength on the moon, is different than on Earth. On Earth, it's approximately 10 newtons per kilogram. On the moon, it's approximately 1.6 newtons per kilogram. The normal force is a support force. So if you're standing on the ground is pushing you up. That is the normal force. It is defined as the force that a surface exerts on an object, and this force is perpendicular to the surface. An example of this is when you stand on a bathroom scale. The bathroom scale is pushing you up, and you can look at the number on the bathroom scale to find out what the normal force is. And that's also your apparent weight. So imagine if you were to put the bathroom scale in an elevator and it's accelerating upward, your apparent weight would be greater than your weight would be because you are accelerating upward. If there is no normal force acting on you, then you would be in what we call weightlessness. You would feel weightlessness and you would be in free fall. So weightlessness doesn't mean you don't have a weight. It just means that there's no support force, no normal force pushing you up. Tension force is defined as the pulling force due to a string, a rope, a chain, cable, etc. And so the direction of the tension force is along the direction of the string. When you see the term ideal string, that refers to a massless string that doesn't stretch. Here's an example of some forces, and this is called what we call a force diagram. Notice that the forces start from the center of mass of the object, and they point in the direction that the force is acting. So here we have a string that's connected to this block, which is on this incline. the force of the string, we call this the tension force. The force of the surface pushing on the block, we call this the normal force. Notice that it's perpendicular to the surface, and gravitational force is always going to be downward towards the center of the earth. And if we know the mass, which is 5 kilograms, we can calculate the gravitational force by taking Fg equal to m times g. Next, we'll take a look at friction forces. So there are two types of friction forces. The first is kinetic friction. This is the force that acts between two surfaces that are sliding past each other, and the direction of the kinetic friction force is in the opposite direction of the motion. The equation for the kinetic friction is mu k times Fn. Fn is the normal force. Mu k is the coefficient of kinetic friction. This tells you how much stickiness there is between the two surfaces. When you use this equation, you'll notice some absolute values because mainly we're looking for the magnitude of the frictional force. And then as far as the direction, you just remember that the direction is in the opposite direction of motion. Static friction is when an object is not moving relative to the surface. So we define it as the force that prevents relative motion between two surfaces. Now, it doesn't mean that it's not moving. For example, you could have a pickup truck and a box in the back of the pickup truck, and the pickup truck is moving, but the box is not sliding relative to the pickup truck. So we want to be careful when we say that the object is not moving. We're talking about the surfaces are not moving relative to each other. The equation is very similar to kinetic friction, but there is a little bit of a difference. So for static friction, it's less than or equal to the coefficient of static friction times the normal force. And notice that it's less than or equal to, because if there's no external force causing it to move, then there's no static friction. If you push it a little bit, there is static friction that has the same amount of magnitude but in the opposite direction. As once you exceed this mu times Fn, this amount right here, then it starts to move. So it's not automatically equal to mu s times Fn. This is what we call the maximum static friction. But if you only push the object with a little bit of force, then you're going to have a little bit of static friction in the opposite direction, balancing the forces. But once you go above mu s times Fn, then the object will start to move. On the left, we have a box on an incline, and this box is not moving. The velocity is equal to 0. So what are the forces acting on this box? I like to always start with Fg because all the objects will have gravitational force pulling on it. So that's going straight down. The normal force is perpendicular to the incline, so it's in that direction. And then the static friction is going to be along the surface, and it's preventing it from sliding down. So the way I like to think about static friction here is, imagine there was no static friction. Which way would the box go? And the box would slide down. So the static friction, to balance that, has to be in the opposite direction. So I know it's going to be towards the top of the ramp. On the right here, this is a box connected to another box through a string, and there's a pulley here. This is called a modified Atwood's machine. And we'll start with the box on the table. So there's gravitational force down, normal force up, there's tension to the right, and if there is friction, the kinetic friction will be to the left. On the right, the mass that's hanging on the string, we have gravitational force down and tension force up. Now, a common mistake that students make is that they think that the tension force here and the gravitational force here are equal, but if this object is accelerating downward, then there has to be a net force. So Ft has to be less than Fg. So don't fall for that trap there. Know that if this object is accelerating, then the forces have to be unbalanced. Let's say that this surface, between the surface and the box, has a coefficient of kinetic friction of 0.2. What is the kinetic friction? Well, if we know the gravitational force is 10 newtons, let's say we're given that, then we know that the normal force also has to be 10 newtons because it's not accelerating up or down. And then we know that Fk equals mu times Fn. Mu is 0.2, Fn is 10, and we get Fk is 2 newtons. Now we'll take a look at Hooke's law. So Hooke's law relates to situations where you have a spring. So it is the force needed to extend or compress a spring by some distance. What it's saying is that force is proportional to that distance. So if you have a spring here and you pull it to the right, there will be a spring force pulling it to the left. If you compress it to the left, the spring force will push it to the right. The equation for the spring force is equal to negative kx. That negative just says that the spring force is in the opposite direction of the displacement. On your equation sheet, it has absolute values. So typically when we use this equation, we're just trying to get the magnitude, and then the direction, we can figure that out because it's going to be in the opposite direction. The spring force will be in the opposite direction of the displacement. K is what we call the spring constant, how stiff that spring is. If you graph the spring force versus the displacement, then the slope will represent the spring constant. More stiff spring will have a bigger slope. A looser spring, less stiff spring, will have a less steep slope. Now we're going to take a look at Newton's first law, which states that an object at rest will stay at rest and an object in motion will stay at constant velocity unless acted upon by an unbalanced force. Another way to think about unbalanced force is the idea of a net force. So if something has a net force, that means it has an unbalanced force. Equilibrium, when you see that term equilibrium, it means that the net force is zero. Whenever the net force is zero, you know that the object is at rest or moving at constant velocity. And you can go the reverse of this. You can reason that if an object is at rest or moving at constant velocity, then it must be in equilibrium. The net force has to be zero. So it goes both ways. Let's take a look at this pie pan here. It's got 1/4 of it cut out, and we've got a ball that we're rolling around. And once it gets to this point, which way is that ball going to go? Is it going to go along path A, continue in a circle, path B, straight ahead, or path C, is it going to roll away from the plate? The answer is B. And the reason it's B is because at this point right here, before it leaves the plate, it's going in that direction. So once the wall's not there, it's going to keep going. It's not going to go A because the wall's not pushing it towards the center here. And it's not going to go C because there's no force pushing it that way. So this is a pie pan, and we're looking from a top-down direction. So once it gets to the edge of the pie pan here, it's going to go straight path B. Another example of Newton's first law is this person on the skateboard. So this person is going to the right, there's a block on the ground, and when the skateboard suddenly stops, the skater continues moving forward, and this is an example of Newton's first law because this person was an object in motion, and so even though the skateboard stopped, the person is going to continue to move in a forward direction until there is an unbalanced force. Next, we're going to take a look at an inertial reference frame. So an inertial reference frame is one from which an observer would verify Newton's first law of motion. Now, I find it more helpful to think about non-inertial reference frames. By understanding non-inertial reference frames, I think it'll help you to understand what an inertial reference frame is. Okay, so here we have a car that's making a turn. And so from the outside observer who is in an inertial reference frame, Newton's first law would hold. But the person inside the car has a non-inertial reference frame. As this person is turning, the person's going to feel like they're getting pushed outward. Even though there's no force from an outside observer, there's no force pushing the person outward. The person feels like they're pushed outward because they were going in this direction, and so their body tends to want to continue moving in a straight line. But the car turns, and that's a non-inertial frame. Now, this person in this car, inside the car, also has a non-inertial frame as well. When the car suddenly speeds up, from the outside observer, we know that an object at rest tends to stay at rest, and so this person's head is going to kind of bob backwards because the person's head was at rest, but the person inside feels like they're getting pushed back, even though there's no force pushing them back. It's just the car is accelerating towards the right. Now we're going to take a look at Newton's second law, which states that acceleration is equal to the net force divided by the system mass. I like to write it this way: net force equals ma when I am solving a problem, but a equals net force over mass is, I think, more intuitive. So if you have a greater net force, you're going to have a greater acceleration. If you have a greater mass, you're going to have a smaller acceleration. We want to remember that anytime you have forces that are unbalanced, you will have an acceleration. The equivalent principle tells us that within a non-inertial reference frame, an observer cannot tell the difference between the sensation of weight and the effects of acceleration. So here's an example. We have this person who is in this room, and it's completely enclosed. There's no windows, and this person is on a bathroom scale. And so this person has a feeling of a sensation of weight. Now imagine another person in the same size room, no windows, they cannot see out. They're also on a bathroom scale, but instead they are in a rocket. They are in outer space, and this rocket is accelerating at 9.8 meters per second squared. Same thing as the gravitational field on Earth. these two people would not be able to tell the difference. They wouldn't know if they're on Earth or in the rocket ship. They would feel the same way. The bathroom scale reading would read the same thing. And so this is the idea of the equivalence principle, that within a non-inertial reference frame, these two people would not be able to tell the difference between whether or not they are on Earth or in a rocket that is accelerating at an acceleration of 9.8 meters per second squared. Now we'll take a look at the center of mass. The center of mass is defined as the average position of all the parts of a system weighted by their masses. The equation is the position of the center of mass is equal to m1x1 plus m2x2 plus ... divided by the total mass. A system's center of mass obeys Newton's second law. What this is saying is that if there is a net force on the system, then the system's center of mass will accelerate. If there is no net force on the system, or the forces are balanced, then the center of mass will not accelerate. The center of mass velocity only changes if there's a net force on the system. Here's the equation for the velocity of the center of mass, and you'll see that it looks very similar to the equation above. This one is not in the equation sheet, but I just wanted to show you and let you see how similar it is to the other equation. So here's a couple examples of the center of mass. So on the left here, top left here, we have an object that is about to explode, break up into pieces. And so this is before it explodes. And then after it explodes, notice that the pieces are flying in all different directions. But the center of mass is still at the same location as long as there's no net force acting on the system. Now, let's say we took a tennis racket and we were to toss it and we were to rotate it flip it as it falls through the air. Notice, even though that it rotates, the center of mass, which I'm representing with this green dot right here, notice how it follows a projectile motion, just as if you were to take a baseball and then toss it through the air, it would follow this path. So what this is telling us is that even though the tennis racket is shaped differently, not symmetrical, one side might have more weight than another side, and shape, differently. However, the center of mass will still follow Newton's second law because there is a force of gravity downward. Vertically, it will accelerate, but horizontally, it's moving at constant speed. Now we're going to take a look at Newton's third law, which states that for every action force, there's an equal and opposite reaction force. Now we want to remember that action-reaction forces always act on different objects, and we refer to these pair of forces as the third law force pairs. Now I want to show you an example of an apple and the earth here, because a lot of times this will puzzle students, which is, how is it that the earth can pull on the apple the same force that the apple pulls up on the earth? So I want to take a moment to explain this. Now I'm going to be using the agent-victim notation to notate the forces. So this FEA means that this is the force of the earth acting on the apple, and this right here is the force of the apple pulling up on the earth. Okay, and so you can see that these forces are equal in opposite direction. Let's first focus on the apple. So on the right here, we have the apple. The force acting on the apple is FEA, and the mass of the apple is very small compared to the earth. And if we take a big number divided by a very small number, we get a big number. So this A is very big. Now, the force acting on the earth, which is the FAE, the force of the apple pulling on the earth, this is the same force as the force of the earth pulling on the apple. However, the earth is way bigger. So I wrote down this really big M. And if you take a number divided by a really, really, really big number, you get a really, really small number. So the acceleration on the earth is very, very tiny. So yes, the force acting on each other is the same. The earth pulling on the apple and the apple pulling on the earth, equal and opposite forces. That's true. However, the acceleration is different because they have different masses. The apple has a small mass, a big acceleration. The earth has a huge mass, a super tiny acceleration. Now I'm going to go through the steps for solving force problems. Step 1, draw the system boundary. We want to make sure we identify what the system is. Even if you don't draw on paper, just mentally you know what it is. Number 2, draw the force diagram labeled. These are labeled arrows that begin at the object. Number 3, indicate positive direction. Make positive, I suggest make positive in the direction of the acceleration, but you can make it in whatever direction you want, but oftentimes that is helpful to do it that way. Number 4, write the equation using Newton's second law. law for each direction. So I'm talking about F equals ma. And number 5, solve for the unknown. Okay, we're going to start with forces at an angle. Here we have a box. We're pulling at an angle theta. We're pulling with the force of F. And we're going to start with our force diagram. So it's on a surface, so we have a normal force perpendicular to the surface. It's going to be up. It's got gravitational force. It's on Earth, and so Fg equals mg. And then it's moving to the right, so friction will be to the left, and kinetic friction is equal to mu times n. We don't break up forces into components where we're drawing the force diagram. If they ask you to draw the force diagram on the free response question, do not break them up into components. Break them up into components somewhere else on the paper, which is what I'm doing on the right-hand side right here. So first, I'm going to make sure all the forces are on the x and y axis. I'm making right positive and up positive, so don't forget to indicate that. And we're going to use a little bit of trig. So the horizontal component is going to be f cosine theta because it's adjacent to the theta, and then the vertical component is going to be f sine theta because it's opposite of theta. I'm going to write down Newton's second law for both the x and the y direction. I'll start with the y direction. That force in the y direction equals may. And so I'm going to first write down all the forces in the positive direction, which is n plus f sine theta, minus the forces in the negative direction, minus mg. Since it's not accelerating up or down, it's going to be 0. If I solve for n, I get n equals to mg minus f sine theta. Now, horizontally, we're going to use f cosine theta here because that's the component horizontally. And what we're trying to solve here is the acceleration. We're trying to figure out what the acceleration is. So we have net force in the x direction equal to f equal to max. And so we have f cosine theta minus mu n, this is the friction force, equal max. Now we're going to substitute mg minus f sine theta for the normal force, and then we solve for a, and we divide m on both sides, and we get f cosine theta minus mu times mg minus f sine theta, parentheses, divided by the mass of the object. Now we're going to take a look at a block that is sliding down an incline with friction, and we're going to first identify our system, which is going to just be the block. Next, we're going to draw our force diagram. Gravitational force is going to be straight down, equal to mg. Normal force is going to be perpendicular to the surface of the ramp, and then Fk is going to be in the opposite direction that the block is moving. The block is sliding down, so Fk is going to be up the ramp, which is equal to mu times Fn. Next, I'm going to indicate my positive direction. I'm going to make down positive and also make perpendicular to the surface going top left also to be positive as well. I'm not going to break my forces into components here. I'm going to do that elsewhere, which is over here. We're going to make sure we do that separately on the free response question on the AP exam. So now we're going to break our Fg into the perpendicular and parallel component. So the perpendicular component, perpendicular to the ramp, is going to be mg cosine theta because it's adjacent to theta. And then the parallel component is going to be mg sine theta because it's opposite of theta. I'm going to apply Newton's second law to the x and y direction. I'll start with the y direction. So net force in the y direction equals ma y. In the positive direction, we have n minus mg cosine theta. In the negative direction, equal to 0 since it's not accelerating in the y direction. So n is equal to mg cosine theta. On the x direction, we have net force x equals max. In the positive x direction, we have mg sine theta, which is right here, minus friction mu times n equals to max. We're looking for the acceleration, and so we're going to substitute the normal force mg cosine theta for the normal force. Notice that the m's cancel out, and we get that the acceleration in the x direction is g sine theta minus mu g cosine theta. You can also factor out the g as well. Now we're going to take a look at a two-body problem. This is a modified Atwood's machine. You have a block here connected to a rope around a pulley, goes down here, and then connects to another block. So when you take a look at two-body problem, we can set our system on one or the other one or both objects as our system. So I'm going to do all three of these so you can see how that works. So first, I'm going to make block 2 my system. I'm going to make down positive, and the forces acting on block 2 are Fg going straight down. We'll call this M2G, and then going up is the tension force. We'll call that T. And notice that these two forces are unbalanced, because in this situation, this scenario, this block is accelerating downward. So be really careful. Do not set these equal to each other. It is accelerating, so they cannot be equal. These forces cannot be equal. Okay. So now I'm going to apply Newton's second law. F equals ma. Force in the positive direction minus force in the negative direction. M2g minus t equals M2a. Solving for t, we get M2g minus M2a. So if you're looking for the tension force, this is how you can solve it if you know the acceleration. Next, we have block 1, which is pull to the right. We're going to make that our system, make right positive. The forces acting on block 1 are Fg, and we're going to call that M1g. Going up is going to be the normal force, pushing up is the normal force, pushing to the right is the tension force, and to the left is the kinetic friction force, which is mu times the normal force. Notice that the tension force here and the tension force here are going to be equal. It's the same string, and the force throughout that string is going to be the same. Now we're going to apply Newton's second law, net force equals ma, and we have the force in the positive direction minus the force in the negative direction. Tension force minus mu n equals m1a. Solving for t, we get m1a plus mu m1g. Now, if we want to solve for the acceleration and we don't know the tension, here's what you can do. You can make both of these blocks as your system, and we're going to apply net force equals ma. So what forces are acting on your system? What net forces? So there is a normal force and there's m1g, but these two are going to cancel out. So the two forces are m2g and mu n. Normally we have our axis is straight. You can think of the pulley as bending our axis. So the object is going to the right and then it's going down. So it's kind of bending our axis here. So in the positive direction is m2g minus, in our negative direction is mu n equals, and be really, really careful here. This m is the system mass. Okay, it's the system mass. So it's m1 plus m2. Notice I drew my system boundary here. That's why that's so important. And then we're going to substitute the normal force with m1g because we know these two are equal to each other. It's not accelerating up and down. And then we're going to divide m1 plus m2 on both sides. And we get that the acceleration is m2g minus mu m1g divided by m1 plus m2. So even though if you don't know the tension, you can still solve for the acceleration. Now we're going to take a look at a force problem, but that also involves Newton's third law. So here we have a hand pushing on block A, which is next to block B. And so block A is also pushing on block B. Now, when you see a problem like this, here's a key tip, really important, which is to understand that the acceleration of this whole system is equal to the acceleration of each of the items, each of the masses in the system. So the acceleration of A is equal to acceleration of B, which is equal to acceleration of the whole system. So if you know this, this is usually not stated in the problem, but if you know that they're accelerating together, that's going to really, really help you out. Okay, so I'm going to break this up into 3 systems, and then we're just going to analyze them. So we'll start with the first one. So we're going to make both of them our system. So net force equals ma. This is the hand pushing on the 2 blocks. The system is ma plus mb times the acceleration. Note that the system mass is ma plus mb. Really be careful of that. All right, now if just A is our system, now we're just looking at just A. We have the hand pushing this block to the right, and then I'm using my H and victim notation here. This is the force of B on A, and notice there's a force pair here. This is the force of block A on B. So these 2 forces are equal in magnitude, but in different direction. Here's the Newton's second law equation for this one, F equals ma. So we have FH in the positive direction, I'm making right positive, minus FBA, which is to the left, equals to, and notice here, my system mass is ma times the acceleration. For block B, the net force equal to ma. The net force here is FAB. This is the force of A pushing on B equals to the mass of block B times the acceleration. And remember, the acceleration of all of these 3 systems are going to be equal to each other. In this video, we're going to cover the second part of Unit 2 for AP Physics 1. We're going to begin by defining uniform circular motion. So when we say that, what we're talking about is an object that moves in a circle at constant speed. And when an object is moving in a circle, it has what's called a centripetal acceleration. This is the acceleration of an object moving in a circular path. And we're going to demonstrate that this acceleration is always towards the center. Now remember that centripetal means center seeking. So when you see that term, it gives us a hint that's towards the center. Here we have an object going in a circle. And you'll notice that the velocities are tangent to the circle. So we have v1 tangent to this point, v2 tangent to this point of the circle. And to find the change in velocity, we can take the vector v2 minus v1. v2 is in this direction. v1 is going to be, the negative v1 will be in the opposite direction that's shown here. So it's going to be going down. And the resultant vector here is delta v, which is going to be in this direction, which is towards the center. So we know that delta v is towards the center. We also know that acceleration equals the change in velocity over time, and the direction of the change in velocity is also the same as the direction of the acceleration. So if the delta v is towards the center of the circle, the centripetal acceleration will also be towards the center of the circle. Now we're going to derive an equation for centripetal acceleration. To do that, we're going to go back to our velocity vectors here, and we're going to label this angle theta. Because v1 and v2 are both perpendicular to this radial line, this angle over here will also be theta as well. I'm going to redraw this piece of the circle over here. This curved line right here is the arc length. It's just the distance of this curved line. And if theta is small, is very small, then we can approximate this curve as a straight line. Now this arc length is equal to vt. V here is going to be the speed of the object and t is the time. And using proportions, we're going to relate this circle to this circle. So we're going to say delta v over v, so here are the two sides of this triangle here, is equal to vt, which is this shorter side of the triangle, over r, which is the longer side of the triangle. And then we can move the v's over, moving this v to the right, and then moving the t to the left. I get delta v over t is equal to v squared over r. And then if we substitute a for v delta v over t, we get that the centripetal acceleration is equal to v squared over r. Now sometimes an object might be going faster and faster in a circle. And if that happens, not only does it have a centripetal acceleration, but it also has a tangential acceleration. And this is the rate at which an object's speed changes and is directed tangent to the object's circular path. So you can imagine like a merry-go-round where it starts to go faster and faster. It started from rest and then it's going faster and faster and faster and faster. So not only does it have a centripetal acceleration towards the center of the circle, it also has a tangential acceleration, which is tangent to the circle. And the net acceleration is the vector sum of the centripetal acceleration and the tangential acceleration. So you add the vector sums of AT and AC, that gives you the net acceleration of the object. As an object moves in a circle, one of the things we can calculate or we can measure is the period. And the period is the time to complete one revolution or rotation. And the unit for this is seconds. We can also calculate its frequency, which is the number of revolutions per second. The unit for frequency is hertz, or capital H little z. The relationship between period and frequency is an inverse relationship. So the period is equal to, and the symbol for period is capital T, period is equal to 1 over the frequency, or frequency is equal to 1 over the period. Now, since the speed is equal to distance over time, for a circle, we can use this equation. V, by the way, V is velocity, but here we're just talking about the magnitude of the velocity, so we're really talking about the speed here, is equal to 2 pi r. So that's the circumference, which is the distance around a circle, so 2 pi r, divided by capital T, which is the period. So using S equals d over t, we can rewrite it for an object going in a circle. To find its speed, it's just the circumference divided by the period, the time to make one complete circle, and we can rearrange it to solve for the period, which would be 2 pi r over v. In order for an object to move in a circle, there must be a centripetal force. This is the net force that causes an object to move in a circular path. So there's a lot of details here that we got to be real careful about when we talk about centripetal force. First, it is towards the center. Second is that it is not a new force. It is any force can play the role of centripetal force, like gravitational force can play the role of centripetal force, tension can play the role of centripetal force, friction or normal, etc. So we got to be real careful that centripetal force is not a new force. It is a net force, which can be played by any of these forces that we've learned previously. To derive the equation for centripetal force, we can take Newton's second law, net force equals ma, combine it with the equation for centripetal acceleration, ac equals v squared over r, and then we get that the net centripetal force equals mv squared over r. Now let's take a look at some examples where objects are moving in a circle, and let's identify what the force is playing the role of the centripetal force and how we would set up an equation to solve a problem like that. So here we have a car moving in a circle. And at this point here, the centripetal force is towards the center. The force that's playing the role of centripetal force is static friction. And even though the car is moving, it's not sliding side to side. And so the static friction is playing the role of centripetal force. Now imagine if there was no static friction, then this car would skid off. As far as the equation, we would substitute the net force, net centripetal force with Fs, the static friction force, is equal to mv squared over r. Here we have a planet going around the sun, and the force playing the role of centripetal force here is gravity force, and the equation would be Fg equals mv squared over r. Here we have a barrel ride, and this is a ride at an amusement park where it spins around, and the force that's playing the role of centripetal force, ROLE, playing the role here, is normal force pushing on this person. So the wall pushing on this person around, that force is playing the role of centripetal force. So we can set that equation as Fn equals mv squared over r. Over here, we have a ball on a string, and we're swinging this horizontally, and so we have tension force because the string is pulling on the ball, and that force is towards the center, and the equation would be Ft equals mv squared over r. Now we're going to take a look at a little bit more complicated situations. Some of these will have more than one force contributing to the centripetal force, and some of these will have components that are contributing to the centripetal force. So let's take a look at this roller coaster. So this roller coaster that's going around, at the highest point, there are two forces acting on it. There is the normal force, and then there's gravity force pushing down. And then if you were to solve this problem, we would set this equal to mv squared over r. Here we have a ball that's swung vertically at the highest point. There's gravity force pulling down, tension force pulling down. So the equation is Fg plus Ft equals mv squared over r. Here we have the ball swinging in a vertical circle at the lowest point, and notice that the Vt is greater than Fg, and that's because the centripetal force, the net centripetal force, needs to be towards the center, so we know Ft has to be greater than Fg. So the equation here is going to be Ft minus Fg equals mv squared over r. We're going to take the force towards the center minus the force away from the center. That's how you figure out how to write down the net force on the left-hand side. Here we have a car going through a dip, and the center of curvature of this dip here is going to be above the car. So the normal force has to be greater than the gravitational force. So we're going to write Fn minus Fg equals mv squared over r. Once again, for the net force, we're going to take the force towards the center minus the force away from the center equals to mv squared over r. Here we have a car going over a hill. There's a gravitational force down, normal force up. The center of curvature of this hill is below, it's going to be down, so Fg has to be bigger than Fn. So our equation will be Fg minus Fn equals to mv squared over r. Now here we have a conical pendulum, so we have a ball on a string that's going in a circle. Some classes will do the flying pig experiment or lab, and the flying pig is going in a circle. And in either case, the centripetal force here is played by a component of the tension force. So this tension force is in this direction at this angle, and the horizontal component of the tension force, which is towards the center of this circular path, is Ft cosine theta, because it's a side next to the theta. So Ft cosine theta for the equation that we would set up for this problem would be Ft cosine theta equals to mv squared over r. Now we're going to take a look at another roller coaster problem, but here's the question, which is what is the minimum speed that the roller coaster needs to make it all the way around? Now, when a roller coaster goes around a loop here, there's gravitational force and there's some normal force. To find the minimum speed to get all the way around, we're going to set the normal force to 0. So this means that it's barely going to get around. And if we set the normal speed to 0, Fg is mg, right? Mg equals to mv squared over r, centripetal force equation. And then if we cancel out the m's, we get v is equal to square root gr. So the square root of gr will give you the minimum speed to make it all the way around the loop. Of course, you can go faster. If you go faster, you're going to have a greater normal force. But if you set the normal force to 0, that's the minimum speed you need to get around the loop. Next, we have a car going around a banked turn. There's gravitational force down. The normal force is perpendicular to the ramp. The centripetal force here is going to be the horizontal component of the normal force. Now, how do I figure out these angles here? So we're just going to use geometry here. So if you take a look at this ramp here, we have theta, right? And if you extend this line all the way through, these two angles are alternate interior angles. So I know these two angles are the same. Now, this forms a right triangle. I'm going to call this alpha. So alpha and theta are complementary angles. They form 90 degrees. They add up to 90 degrees. This is a triangle and right triangle. So I know this angle and this alpha has to also equal 90 degrees. So this also has to be theta. So I know this is theta, and so the horizontal component of Fn is going to be Fn sine theta. So if you're working on this problem, you would substitute for the net centripetal force. You would write Fn sine theta equals to mv squared over r. Now we're going to take a look at Newton's law of universal gravitation, which tells us that all masses attract each other with a gravitational force. Now this force is always attractive, and the two forces are going to always be equal and opposite direction. So this reminds us of Newton's third law. And it doesn't matter if one object is bigger than the other, the forces will always be equal in an opposite direction. And I'm using this dotted line right here just to indicate that these are Newton's third law force pairs. These are force pairs. These are action-reaction forces. The equation for Newton's law of universal gravitation is Fg equal to big G m1 m2 divided by r squared. M is the mass of the object. Big G is the gravitational constant, 6.67 times 10 to the negative 11 Newton meter squared divided by kilogram squared. So this is called a constant because it's the same anywhere in the universe. It doesn't depend on location. And then r is the distance between the centers of the two objects. So if you're dealing with large objects, we're measuring from the center to the center of the two objects. Gravitational field is the space of gravitational influence. And there are two ways to measure the gravitational field. One is to place a test object in the field. So for example, you could have an apple. You measure the weight of the apple divided by the mass of the apple. That will give you the gravitational field at that location. Another way to measure gravitational field is to use the mass of the object, the large object that is generating the gravitational field. And we can derive this equation by substituting Newton's law of universal gravitation for Fg. So remember, Fg is big G times m1, m2 divided by r squared. Notice that the little m's cancel out, and that leaves us with little g is equal to big G times big M divided by r squared. Big G is the gravitational constant. Big M is the large mass generating the gravitational field. So usually this would be like a planet, it could be the moon, it could be the sun, but generally it's a large mass, and R is going to be the distance from the center of that large mass to the location that you're measuring the gravitational field. Since we can't directly see gravitational fields, one of the ways we can visualize it is to use what are called gravitational field lines. And here you can imagine a large planet, and we have lines. These lines are representing gravitational fields, and we call these lines gravitational field lines. Where the lines are closer, such as over here, we have a stronger gravitational field. Where the lines are further apart, we have weaker gravitational fields. So this is just a way for us to visualize the gravitational field, where it's stronger, where it's weaker. The direction of the gravitational field points towards the direction that a mass in the field would get pushed. So if I put an apple over here, it would get pushed in this direction, and so the direction of the gravitational field here is going to be in that direction. Now this is a graph that shows you as you're moving away from the Earth. So here's the surface of the surface of the Earth right here. And this tells you the gravitational field at the surface. So on Earth, it would be 9.8 newtons per kilogram. And then as you're moving away, you can see that it decreases, and you can see that it's an inverse relationship. It's actually an inverse squared relationship. The gravitational field near a planet is numerically equal to the free fall acceleration. So when we talk about gravitational field, we say that it's 9.8 newtons per kilogram. It tells us how much force, gravitational force, is pulling on the object for every kilogram that it has. The acceleration due to gravity is also 9.8 meters per second squared. Now, numerically, these two are the same. And unit-wise, you could see that they are equivalent because newtons over kilogram is equal to, and we know that newtons is a kilogram meter per second squared. Newton is a derived unit, which is equal to kilogram meter per second squared. And the kilogram, you can see that they cancel out, so which leaves us with meters per second squared. So these units are also equal to each other. Now we're going to compare inertial mass and gravitational mass. Inertial mass measures the object's resistance to changes in motion when a force is applied. So if we exert a force on this green mass and measure its acceleration, we can calculate the inertial mass by taking the force divided by the acceleration. For gravitational mass, this determines how strongly an object interacts with a gravitational field. So on Earth, we know that the gravitational field is 9.8 newtons per kilogram. And if we weigh this green mass here and get its Fg, we can take the Fg divided by the gravitational field, and that would give us the gravitational mass. We could also do an experiment like the Cavendish experiment, and using this, we can measure the gravitational force between the spheres. We know the gravitational constant, and if we know one of the masses, either the green or the yellow spheres, and we know the distance between the spheres, we can calculate the mass of the other sphere, and that mass would be its gravitational mass. Now, experimentally, the inertial mass and the gravitational mass are always found to be numerically equivalent. So although we have different ways of measuring these masses, the number associated with these masses are always the same. For both Newton's law of universal gravitation and the gravitational field equation, you'll notice that there's an inverse square relationship. And so we can say that the gravitational force is proportional to 1 over r squared, or you can say that the gravitational field is proportional to 1 over r squared. And so I want to take a moment to talk about the inverse square law. So if the r doubles, the Fg will change by a factor of not 1 over 2, so that's a common mistake. You'll notice there's a square there. It's going to be 1 over 4. Okay. If the r is halved, so if this bottom part is halved, right, we need to flip that, right, because it's in a denominator. So it's going to change by a factor, not 2. So that would be a common mistake. So we think half, reciprocal of half is 2 over 1, but we need to square that. So it's going to change by a factor of 4. Next, we're going to derive orbital speed and period. Now, this is really cool because here we're going to combine our understanding of centripetal force equation and Newton's law of universal gravitation. So when an object is going around the planet, let's say we have a moon that's orbiting the planet, we can set the net force. The net centripetal force here is going to be a gravitational force. And the gravitational force, we could use Newton's law of universal gravitation, big G, m1 times m2 divided by r squared. So we set that equal to mv squared over r. The m's will cancel, and one of the r's will cancel, and that gives us big G, big M over r is equal to v squared. Now be real careful that this big M is the central mass. In this case, the central or the large mass is the planet. And if we solve for v, we get v is equal to square root big G times big M divided by r. This gives us the orbital speed. So this is the speed you would need to stay in a circular path. Of course, if you go faster, then you're going to go in an elliptical path. If you go slower, you also go in an elliptical path. If you go too slow, you're going to crash into the planet. Now, we know that the speed of an object going in a circle is the circumference divided by the period. And if we plug this into v, and I'm plugging that into v here on the right-hand side, and we square it because this v is squared, we get 4 pi squared r squared over t squared. And if we solve for t, we get this equation, t squared, this is the period square, is equal to 4 pi squared over big G over times big M times r cubed. And so you'll notice that the period squared is proportional to the radius cubed. This is the radius of the orbit, and this is Kepler's third law. Now we're going to use Kepler's third law to answer a experimental design question, one that you might see on an AP Physics 1 exam. So you might be given some data, which include the period of an object going around, maybe the moon going around a planet, and then also the radius of the orbit of the moon going around the planet. And they're asking you to calculate what is the mass of the planet. So if you graph the period squared versus the radius cubed, you get a slope, and that slope is going to represent this value right here, 4 pi squared over big G times big M. And how do I know that? Because this has the format of y equals mx plus b, the slope-intercept equation. And the slope right here, the m right here, is the 4 pi squared over big G times big M. When you are calculating the slope, we want to be very careful that we don't just use data points. We want to make sure we use points that are on the best fit line. So the yellow right here are your data points that you got from the exam question. And then so you draw your best fit line, which is a straight line that's as close to as many dots as possible, but it is not connecting the dots. And then you're going to pick 2 points, and here I picked these 2 blue points. These 2 points are the ones I'm going to use to calculate the slope. So the slope equation is y2 minus y1 divided by x2 minus x1. You could also use rise over run as well. And then we know that the slope is 4 pi squared over big G times big M. And so setting the slope number that I got, I'm going to substitute that for the slope. I'm going to solve for m, so I'm going to isolate the m, substitute the slope number here, and solving for m, that will give us the mass of the planet. In this video, we're going to be reviewing work, energy, and power. This is Unit 3 of AP Physics 1. We're going to begin with the concept of work. Work is the transfer of energy due to a force applied to an object, causing displacement in the direction of the force. And work is a scalar. It only has a magnitude, no direction. The equation for work is force times the displacement times cosine theta. The unit for work is joules, and a joule is equal to a Newton meter. Now let's take a look at examples where work is positive, negative, or zero. So if the force is in the same direction as the displacement, then the work is going to be positive. If the force and the displacement are in opposite directions, then the work will be negative. If the force and the displacement are at an angle, then we will need to use our equation, work equals FD cosine theta. Theta will be the angle between the force and the displacement. If the force and the displacement are perpendicular, then the theta is going to be 90 degrees, and cosine 90 degrees is 0, so the work done will be 0. So why do we care if work is positive or negative or 0? Well, work tells us the transfer of energy going into or out of a system. So a positive work means energy is transferred into the system, and negative work means energy is transferred out of the system. We'll see more of the significance of this later as we talk about energy. On a force versus displacement graph, the area under the curve represents the work. When I say area under the curve, I mean the area between the graph and the horizontal axis. This area can be positive or it can be negative. If I wanted to find the net work, I need to take into account the positive and the negative section of this graph. Work can be done by conservative forces or non-conservative forces. So we're going to take a moment to compare these two. Work done by a conservative force is path independent. So here's an example. So here I have a green box that I'm going to lift up, and we're going to focus on gravity force because gravity force is an example of a conservative force. So we're going to lift it up. Gravity force will be doing negative work because the object is moving up while gravity force is pushing it down. So the directions are opposite, so the work is negative. Then I'm going to move the box to the left because the force and displacement are perpendicular. The work done by gravity is 0. Then I'm going to move the box down, and the work here is positive because the force and the displacement are in the same direction. Now, whether I move the box up, to the left, and down, or if I move the box directly to the left, the total amount of work is going to be the same. In this case, it's going to be 0. So we say that it's path independent. And furthermore, if I move the box up, left, down, and back to the right, back to its initial state, we call this a closed loop. The net work done on the object is going to be 0, the net work done by the gravity force. Another example of a conservative force would be a spring force. Now let's contrast this to work done by a non-conservative force. So example of non-conservative force would be something like friction or air drag. So here I have my green box and it's on a table, and a work done by a non-conservative force is path dependent. So let's say I were to push this green box up forward here to the right and back down over here. That amount of work done by friction is different than if I had taken the box and moved it to the right. So we say that it's path dependent. And if I were to move this up, right, down, and back to the left on the table, back to its initial state, we refer to this as a closed loop. The work would not equal to 0, so it would be a non-zero amount of work. Next, we're going to take a look at energy. So energy is the ability to do work. And energy is a scalar, which means that it has a magnitude but no direction. The unit for energy is joules, and there are different forms of energy. I like to think of these as different ways that energies are stored. So for example, with gravitational potential energy, this is energy that's stored in the gravitational field, and this only occurs when there's more than one object. So with gravitational potential energy, we're looking at the object Earth system, and the equation for gravitational potential energy is mgh. This is when the object is near the Earth's surface. Once again, it assumes that the Earth is in your system, and we're assuming a constant gravitational field. Next, we have kinetic energy, and kinetic energy is energy stored in the motion of the object, and it's equal to 1/2 times the mass times the speed squared. And this depends on your reference frame, because if you were to observe something moving, it depends on where you're observing it from. If you see a car driving by at 60 miles per hour, you observe that speed. But if you're in the car, you observe that the car is moving at 0 miles per hour because you're moving with the car. So kinetic energy does depend on your reference frame. Then next, we're going to take a look at energy stored in a spring. So this is a spring or elastic potential energy, and it's equal to 1/2 K. K is the spring constant times delta X squared. So the delta X is the distance the spring has been stretched or compressed from the equilibrium position. Next, we have the rotational kinetic energy. This is energy stored in the rotational motion of an object, and it's equal to 1/2 times the rotational inertia, or the moment of inertia, times the angular velocity squared. And then lastly, we have the gravitational potential energy. This is the more general equation. So let's say you're not on the surface, you're further away, and it's equal to negative big G, the gravitational constant, times m1 times m2 over r. m1 will generally be a large mass, such as a planet, and the other mass will be a smaller mass object. Mechanical energy refers to potential and kinetic energy. By the way, potential energy sometimes we'll use the symbol capital U, and for kinetic energy sometimes we'll use the symbol capital K. Mechanical energy is conserved when only forces doing work on the system are conservative forces. Examples of conservative forces are gravitational force and spring force. Just a quick reminder of non-conservative forces. Those would be forces like friction or air drag or applied forces. And that's because these forces will transfer some of those energy into heat and sound energy. Now, when we talk about conservation in physics, we're saying that it doesn't change. So mechanical energy, we're talking about how the initial total mechanical energy is equal to the total final mechanical energy if only the forces doing work on the system are conservative forces. We can represent it with this equation here, that the potential energy plus the kinetic energy is constant. Now the potential energy could change, the kinetic energy could change, but the total amount is constant. We can also write it as Ui plus Ki equals Uf plus kf. Let's take a look at some examples. Here's a pendulum. I'm pulling to the left and I let it go, and it's falling. The potential energy, the gravitational potential energy is decreasing, but the kinetic energy is increasing, but the total amount of mechanical energy stays constant. Here we have an apple. We're dropping the apple as it falls. The gravitational potential energy decreases, but the kinetic energy increases, but the total mechanical energy, once again, is constant. Here we have a block on a spring. If we pull it to the right and we let go, it has elastic potential energy. It's going to move to the left, and that elastic potential energy is going to decrease, but the kinetic energy is going to increase. So once again, the total mechanical energy is constant. Internal energy is heat energy that causes an increase in the temperature of the system. An example of this is work done by friction. And we can calculate work done by friction by taking the force of friction times d, the displacement, times cosine theta. So here's an example. I have a block here that's moving to the right. So maybe I pushed it initially, but now it's not being pushed by my hand. It's just slowing down on the surface because it's on a rough surface, and it's moving to the right. However, friction is to the left, and theta is going to be 180 degrees because it's measuring from the frictional force to the displacement, and cosine 180 degrees is -1. So work done by friction is going to be negative. The significance of this negative is telling us that it's removing energy from the system. And although mechanical energy is not conserved, we can still use the work energy principle when we're dealing with work done by non-conservative forces. Ui, the initial potential energy, plus Ki, the initial kinetic energy, plus the work done by the non-conservative force, in this case it's friction, is equal to the potential energy final plus the kinetic energy final. Next, we're going to look at the general equation for gravitational potential energy. The reason we wouldn't just use mgh is because as you move further and further from the Earth, g is no longer 9.8, and the gravitational field is not constant. And so instead, we have to use this general equation for GPE, which is negative big G, which is the gravitational constant, times m1 times m2 divided by r. One of the masses will be a mass of a large mass like a planet, and then the other object will be a much smaller mass. Here we have a graph representing this relationship. We have gravitational potential energy versus the distance of the object as you move away from the surface of the planet. Here RE is the radius of the Earth, and as you move further and further away from the Earth, you'll notice that the gravitational potential energy increases. Although it doesn't increase in magnitude, it increases in that it becomes less and less negative. So as the distance increases, gravitational potential energy increases, it becomes less negative. Also, the gravitational potential energy is equal to 0 as r approaches infinity, and only changes in gravitational potential energy matter in solving most problems. You may have noticed that there's a negative sign in front of the equation, and that negative sign indicates that energy is required to separate masses to infinity. And without that energy, the mass would just fall back to the planet. So now we're going to try to connect the concept of work and energy through what's called the work-energy theorem. And this states that the net work done on an object is equal to its change in kinetic energy. So the work net equals to delta Ke, which is equal to the final kinetic energy minus the initial kinetic energy. And we know that kinetic energy is equal to 1 over 2 mv squared, so we can write it as the work net equals to 1 over 2 mv final squared minus 1 over 2 mv initial squared. When the net work done is greater than 0, this means that the kinetic energy is going to increase and the speed of the object will increase as well. When the net work is less than 0, that means the kinetic energy will decrease and the speed will decrease. If the net work is equal to 0, then the kinetic energy and the speed will be constant. Now we're going to apply what we've learned about energy and work to orbits. We're going to start by looking at circular orbits. Here we have a satellite orbiting the Earth, and you'll notice that the satellite is moving in a direction perpendicular to the gravitational force. So the displacement of the satellite and the force acting on the satellite are perpendicular, so the work done is going to be 0. Since the work done is 0, the work energy theorem tells us that the kinetic energy is not going to change. So the kinetic energy is going to be constant. Since the kinetic energy is constant, the speed of the satellite is also constant. The gravitational potential energy is also going to be constant because the orbital radius is constant. Now, since only conservative forces are acting on our system here, the total mechanical energy is constant, which means that the sum of the kinetic energy plus the gravitational potential energy is going to be constant. Because that there are no external forces doing work, no energy is added or removed from the system. Now we're going to take a look at elliptical orbits. And here we have a satellite going around the Earth, and we're going to start with the position on the left here, and the green dot represents the satellite. It's moving in this direction, and there's a gravitational force towards the Earth. And you can see that there is a component of the gravitational force that is in the opposite direction of velocity. That means that the gravitational force, that component, is doing negative work on the satellite, which means that the kinetic energy of the satellite is decreasing, which means that the speed of the satellite is decreasing. And so we say that the kinetic energy is not constant and that the speed changes. On the right-hand side of our orbit here, the satellite is moving this direction, gravitational force is this direction. And you can see that there's a component of the gravitational force in the direction of the velocity. And so at this point, there is positive work done on the satellite by this gravitational force. And this positive work is going to cause the kinetic energy of the satellite to increase. And so if the kinetic energy of the satellite increases, that means the speed of the satellite also increases. Gravitational potential energy is not constant because the orbital radius of the satellite and of the satellite's orbit is changing. And the total mechanical energy, GP plus KE, is constant because only conservative gravitational forces are acting on the satellite. Escape velocity is the minimum speed required to escape a planet's gravitational pull. In this diagram here, we have a planet. Let's say this is Earth, and we have a green dot. Let's say this is a baseball. And we were to toss the baseball up into the air, you know that the ball would fall right back down. But imagine if you could build a robot that could throw a baseball super fast. The question is, how fast would this robot have to throw the ball into the air so that it doesn't get pulled back towards the Earth? And we're assuming no additional forces, so there's no propulsion on the baseball and that there's no air resistance. To calculate the escape velocity, we can set the total mechanical energy equal to 0. And the gravitational potential energy is negative big G times the mass of the planet times the mass of the baseball divided by the distance between the baseball and the center of the planet, plus 1 over 2 times mv squared. Set that to equal to 0. You'll notice that the masses will cancel. The v squared will equal to, if I multiply 2 on both sides, I get 2 big G times big M divided by R, square root on both sides. We get that the escape velocity is equal to the square root 2 times the gravitational constant times the mass of the planet divided by R, the distance between the ball and the center of the planet. Power is the rate at which work is done. To calculate average power, we can take the work done divided by the time. Since work is related to the change in energy, the average power is equal to delta E over T. The unit for power is watts, and a watt is equal to a joule divided by a second. We can also calculate power by substituting the equation for work, which is FD cosine theta divided by T. And we know that D divided by T is speed. We're going to use V to represent speed here. So the instantaneous power is equal to the force times the speed of the object times cosine theta. When solving energy problems, it's helpful to use an LOL energy chart. Here we have a block 5 kilograms sliding down a ramp which is 3 meters long, and we want to find out what the velocity of the block is at the bottom of the ramp. So first we're just going to qualitatively represent this, and then next we're going to mathematically solve it. So initially it has only gravitational potential energy. And this circle represents the system of that we're working with, which is the block and the ramp and the Earth. And as it's sliding down, because of friction, some of this energy is transferred out of the system. And at the bottom of the ramp, we have some kinetic energy. Notice that the initial part has 3 blocks, and then the final has 2 blocks, and that's because 1 block of energy was transferred out. Now, this is not going to be completely mathematically accurate. It's just qualitatively helping us to set up the problem and understand what's going on. That you start off with gravitational potential energy. Some of that energy gets converted into heat and transferred out of the system. And then at the end, we have some kinetic energy, but that kinetic energy is less than the gravitational potential energy that we started with. Now we're going to mathematically solve this problem. So this block is going to slide down the ramp, and we want to find out what is the final velocity of this block. We're going to need to know the height of this ramp, and we can use trig to solve that. Sine 30 equals opposite, which is h, divided by the hypotenuse, which is 3 meters. H is 3 times sine 30 degrees, which is 1.5 meters. Next, we're going to need to know the initial gravitational potential energy, which is equal to mgh. The mass is 5 kilograms, g is 9.8. The height is 1.5, which we just solved. The gravitational potential energy initially is 73.5 joule. The kinetic friction is equal to mu times n. And here we have a force diagram. We have mg going straight down. Normal force is perpendicular to the ramp. You can see that there is a component of mg that is along the same axis of the normal force. And so the normal force is equal to mg cosine theta. So I can substitute that in here. The reason I know that normal force is equal to mg cosine theta is because it's not accelerating along that axis. And we can calculate that and we get 8.48 newtons. Now we can use our conservation of energy equation. Initial kinetic energy plus the initial gravitational potential energy plus the work done by friction is equal to the final kinetic energy plus the final gravitational potential energy. We're going to substitute our numbers that we've calculated. So the initial kinetic energy is 0. The initial gravitational potential energy is 73.5 joules. The work done by friction is negative 25.4. And we calculated that here, which is because work is force times displacement. We have the force of friction times the displacement. And it's negative because the friction and displacement are in the opposite direction, so we have a negative number here. The kinetic friction, the final kinetic friction, we're solving for that, and the gravitational potential energy at the bottom of the ramp is going to be 0. And solving for VF, we get VF squared is equal to 19.2, square root both sides, we get that VF is equal to 4.39 meters per second. In this video, we're going to review linear momentum for AP Physics 1. We're going to start by defining momentum. So momentum is the product of an object's mass and its velocity. Momentum is a vector, which means it has a magnitude and a direction. And the equation for momentum is P is equal to mv. Note that the direction of the momentum is in the same direction as its velocity. Since the unit for mass is kilogram and unit for velocity is meters per second, the unit for momentum is kilograms meters per second. Here we have a large truck and a small car, and they have the same momentum. The large truck has a large mass and the little car has a small mass, but if they have the same momentum, that means the large truck has a smaller velocity and the small car has a large velocity. So if their mass times velocity is equal to each other, we say they have the same momentum. Now we're going to define impulse. Impulse is the product of the average force and the time interval during which that force is exerted on the system. Impulse is a vector, which means it has a magnitude and a direction. The equation for impulse is J, sometimes we use the symbol I, but often it will be capital J, is equal to average force times the time interval. The unit for impulse is Newton seconds, and because the unit for force is newtons, and the unit for time is seconds. On a net force versus time graph, the area under the curve represents the impulse. You can also have a negative area that would represent a negative impulse. Let's take a look at an example. Here's a bat that hits a baseball. The bat exerts a force on the baseball, and the force on the baseball times the time interval that the bat is pushing on the baseball is equal to the impulse. Now, because we know about Newton's third law, how there's also a reaction force here, which is equal but in the opposite direction, and the time interval will be the same. That means there's going to be an impulse on the bat that is equal to the impulse on the baseball, except they're in opposite directions. Now we're going to connect momentum and impulse. The impulse momentum theorem tells us that the impulse exerted on an object is equal to the change in its momentum. So we're going to start with Newton's second law to derive this relationship. F net equals ma. We know that the acceleration by definition is the change in velocity over the change in time. So we can write this as F net equal to m delta v over delta t. If I move the delta t to the left, I get F net delta t is equal to, on the right-hand side, I get m delta v. I can rewrite this as mv final minus mv initial, because delta v is just final velocity minus initial velocity. And we have a name for mv. We call this momentum, and the symbol for momentum is p. And so we can rewrite this as p final minus p initial. So on the left-hand side, we have F net delta t, which is impulse. The symbol for impulse is capital J. On the right-hand side, we have the change in momentum, which we can write as delta p. So impulse is equal to the change in momentum. This is the equation for impulse momentum theorem. Now, if we go back to this equation up here, and if I move the delta t to the right, if I divide delta t on both sides, I get F net is equal to delta p divided by delta t. And this is significant because if we ever get a graph, a momentum versus time graph, then we know that the slope of that graph represents the net force. Next, we're going to talk about the conservation of momentum. I'm going to start with the impulse momentum theorem that we just talked about. And impulse is capital J is equal to the final momentum minus the initial momentum. But if the impulse is 0, there's no net force acting on the system, then we have on the left-hand side 0 is equal to P final minus P initial. Moving that Pi to the left, I get Pi equals Pf. So conservation of momentum is very useful when there is no impulse on the system, no net force on the system. And we can rewrite Pi equals Pf as m1 v1 plus m2 v2. This is the momentum of the objects in your system before the collision. And then m1 v1 prime plus m2 v2 prime. This is the momentum of the objects in your system after the collision. And sometimes we might have an explosion, which we'll talk about in a little bit. So momentum is conserved if there is no net external force acting on the system. What we mean by conserved means that it stays the same. So the total initial momentum equals the total final momentum if there's no external force acting on the system. Conservation of momentum is very helpful in collisions, especially when there are no external net force acting on your system. There's no impulse on your system. So we're going to take a look at some different types of collisions. We're going to start with elastic collisions. In an elastic collision, two objects collide and their initial momentum, total momentum, is equal to the final total momentum. The total initial kinetic energy is also equal to the final kinetic energy. Example of this would be like billiard balls, although in real life you do have some energy loss because it's converted into heat. Next, we have inelastic collisions. Once again, these are objects that are colliding, hitting each other, and the momentum is also conserved. So the initial total momentum equals the final total momentum. However, there is some kinetic energy loss. So maybe some of that energy is lost and transferred to sound energy or heat energy, or maybe it may have deformed the object. Example of this would be a car crash. Third, we have a perfectly inelastic collision. This is when the two objects stick together. Their momentum is still conserved, though the initial total momentum equals the final total momentum. There is maximum kinetic energy loss. And an example of this would be like a clay ball and a block. They hit each other and they stick together. Next, we're going to take a look at an explosion. So in an explosion, internal forces are moving objects in the system apart. So here we have a spring and we have these two carts in our system. And momentum is conserved as long as the system is isolated, which means that there are no net external forces. So we're assuming that there's no friction, for example. We're going to make right positive, and if momentum is conserved, that means the initial momentum equals the final momentum. Because initially it's not moving, I'm going to write 0 on the left, and then after it explodes, the two carts are moving away from each other. On the right, we have cart M V2. The momentum of the car on the right is going to be M times V2, and the momentum of the car on the left will be 2M, that's the mass of the cart, times V1, that's the velocity of the cart. And we're going to do minus because it's in the negative directions. We're going to move the 2M V1 to the left, and notice that the M's cancel out. And we see that V2 is equal to twice the velocity of the cart on the left. Now we're going to take a look at the center of mass. And the center of mass concept is helpful because sometimes you have all these different objects or particles in a system, and this can often simplify the problem. The center of mass is the point at which the entire mass of a system can be considered to be concentrated. And the equation for the center of mass is xcm equal to m1x1 plus m2x2 plus dot 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 divided by m1 plus m2 plus dot dot dot. On the bottom, essentially, you have the total mass. If you divide t on both sides, we get x over t, x over t, x over t, and we know that that is time, it is velocity. And so the center of mass velocity is equal to m1 v1 plus m2 v2 plus dot 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 divided by the total mass. Now we know that m1 v1 is just momentum. So if you add up the total momentum, that's the number you would get at the top. And if you take the total momentum divided by the total mass of your system, you get the velocity of your center of mass. If there's no external net force, then the center of mass velocity is constant. And now we're going to work through the classic problem of the man on a boat. So here we have a man on a boat. He's going to be walking to the left, and as he walks to the left, his feet will be pushing the boat to the right. Our system here is going to be the man and the boat, and the forces on our system is Fg, the force of gravity, and Fb, the buoyant force. The length of the boat is L, and the center of mass of the man and the boat system is going to be at this location here. And the half of the length of the boat, which is the center of mass of the boat, is going to be right here, which is going to be L over 2. So to calculate the center of mass of our system, we're going to use our center of mass equation, which is equal to the mass of the boat times because the boat is an extended object, we're going to treat it as if all the mass were at the center of mass of the boat, so which will be right here, which is L over 2, plus the mass of the man times the location of the man, which is going to be the length of the boat, so that's going to be capital L, divided by the total mass, the mass of the boat and the mass of the man. Now the person is going to walk to the left. As the person walks to the left, the person's pushing the boat with its feet to the right. So the boat's going to move to the right, man moves to the left. And the man is going to now be at a location X, which we'll call X. And the center of mass, now we're going to call it XCM prime. And we're going to use our center of mass equation once again after the person has walked to the left. So we're going to take the mass of the boat times the location of the center of mass of just the boat. So that's going to be L over 2 plus X, because now it's moved to the right a distance of X, plus the mass of the man times the location of the man, which is going to be X, divided by the total mass. Now, since there are no external net forces acting on our man-boat system, the center of mass before the man walked is equal to the center of mass after the man has walked all the way to the left. And so this is the key idea right here. So we're going to set these two equations equal to each other, and then we're going to solve for x. So after we set these two equations equal to each other, we notice that the total mass on the bottom of the fraction will cancel out. That leaves us with ml over 2 plus ml is equal to, and I'm going to multiply the mass here, mx plus ml over 2 plus mx. And so the ml over 2 gets canceled out. That leaves us with ml equal to x times the total mass. Mass of the boat plus the mass of the man. I'm going to next divide the total mass on both sides. So it's going to cancel out on this side. So X is going to equal ml over the total mass. M is 70 kilograms. The length of the boat is 2.5. The mass of the boat is 100 kilograms, and the mass of the man is 70 kilograms. And we get an answer of 1.03 meters. So after the person walks all the way to the left, the person will be at a location of 1.03 meters.